Good afternoon. Couple of administrative items. We're going to begin lecture 10 material today. About the final, what I'm going to implement, there's some concern about people recruiting other people to take their exam. So what I'm going to do, I'm going to try to do this is before you guys take the exam. Yeah, so my plan is, hold on, let me just get through this. What I'm going to do is have each of you send me a picture of your City College ID. I'm going to share a link to a Dropbox folder. And let's see. I'm going to need each of you to take a picture of your ID, and then we will cross-check. The camera image on the 24th with your ID. Now, I understand some of you may find this annoying, but I've heard enough stories that when I heard some of the stories about what was going on with exams, it upset me, and so BME 205 student IDs.
So, Professor, you want the ID to be part of the picture of the paper?
No. Ideally, I would like you to send me your picture ID before the exam so that I have it on file, so that me and the TAs and the FBI agent that I've hired to help me with the exam, just kidding, will look at your face and look at the ID during the exam. I don't want the picture, we need agreement between the ID that you provide me, the City College ID beforehand, ideally, and the camera image during the exam. Just so that we know. I know that 99% of you write your own exams, but I know that not everyone does. And so I'm not, I thought of what's like a, let me see how I share this folder. Share link.
Professor, this is actually my first semester, so I don't have my ID yet. But I have my previous college's ID.
Yeah, that's fine. Previous college ID is fine.
Okay.
Yeah, you can use a different school ID.
It's the same thing for me. I don't have like any school ID at all currently. Is there anything I could do, like show my permit or something like that?
I need something with your picture. Do you have a state ID?
I have a permit, like a legal permit, like a learner's permit.
Oh, that's what you meant by permit. Yeah, sorry, sure. That's perfectly fine.
Okay.
Yeah, so yeah, I understand. Obviously, those of you that don't have your college ID yet, then just show me a piece of ID with your name and face on it. I'm trying to figure out how to. I have too many Dropbox accounts now, and creating link. I'm gonna put it in the Zoom meeting. I'm also gonna put it on the Blackboard. Oops. Okay. Copy link. Thank you. Okay. Alrighty, so in terms of what you can expect on the exam, it's going to be a different format than the midterm. It's going to be it's going to be a computerized exam. It's going to be you're going to be allowed to use a calculator. You're going to be allowed to use pencil and paper. But you will be answering. I have a software that I'm going to use for making the exam online. And so for some of the questions, the solutions will be uploaded. Just again, the software, the online software has a feature that you can take a photo and upload a file. And so that's what you'll do for the problems. And then for the multiple choice, you'll just select the right answer. So it's like Blackboard, but there's some features that I want to use that aren't on Blackboard. And so I'm still working out. Basically, I wanna have some level of asynchrony among the questions and the students. So I don't want everyone to be doing the same question at the same time. That's one thing. And the time limits is another thing. I'm kind of going back and forth about the whole time limits thing. It sometimes it's worked and sometimes it's made people stressed out. And so the idea of a time limit is that you're on question one, like if you've ever taken like the GRA or something, the GRE, I guess it's called. It's been so long. Like the GRE, if you ever took it, it's like you take you're presented with a question, you have to answer the question, and you don't move on to the question until you answer that question. And then there's a time limit for every problem. So I'm thinking about something like that, just to try to make it more fair for everyone. But I haven't decided on the exact format yet. I know what I want to test on. It's pretty standard. For the final of this course, it's always the same. There's one first order circuit, there's one second order circuit, and then there's two questions from lectures 9 and 10. And so I'm going to share a previous exam for you guys to just work off of, so that you know exactly what to expect. But the format I haven't decided upon, even though the content is pretty much is fixed, but I don't know how I'm going to present it to you, other than I don't want to do Blackboard. And I need to see everyone's ID beforehand. I'd like to think that you guys are a really awesome class, but so it may be just that the performance of this class is just statistically higher than it has been in the previous years, but it's also possible that during the midterm grades were a bit inflated for alternative reasons. The midterm was that had a very high average. Can we make, yeah. So for the software, yeah, absolutely. I always do that. I always have this, I always make like a test run, because some people will have problems logging onto the software and things like that. There is no good way of of administering exams online. I'm looking forward to, if you lose connection. I mean, if you lose connection, if you lose an internet connection, well, let's see. The software that I used last year for the exam, yeah, the same thing with the software I used last year for the exam. It saved every time you answered a question, it saved your progress. And and who knows, maybe I'll figure out a way to use Blackboard. It's going to be the same thing though. Like you're not going to have to start from the beginning. Now, if you do lose your internet connection during the exam, I mean, that presents a problem, not just for the exam, but also for the Zoom, the actual video of you taking the exam. So I think the thing to do in that case is to, and I hope it doesn't happen, but if it does, what I would ask you to do is to take a photo of all the work that you have in front of you, like the paper work that you did, and then send it to me with that time, with the times, so that I can send me an email with a timestamp showing me your work at that time, so that afterwards, did I get your upload? Oh, let me check. You guys are fast. Nah, it's still empty. It could be Dropbox. Hold on. Let me see if I have to set some properties. People with a link can view. Okay, hold on. I'm gonna fix this. Settings. I want everyone to have access. People with this link can view. What a pain. Wait, hold on. Let me see. There's got to be a better way around this. Let me try my City College email. Request files. That's how you do it. Okay, so I've done something else. Yeah, I know it's not gonna let you upload. I'm not tech savvy. Here we go. That should work though. That's a Dropbox link that is specifically intended for people to share data. Okay, so I'm gonna give you more info on the exam next Monday. I gotta start teaching. Don't wanna leave. We're gonna do lecture 10. It's not hard. And it involves using phasers. I feel like it's a small turnout today. It's not a good sign. I don't know if you guys are just burnt out from the semester or
Burnt out from the semester and from the homework, and I think everyone is afraid not to finish it before the due date.
oh, well, I can extend it a little bit more. It's fine.
That would be helpful because I don't know everyone I know and like.
No, it's fine. I'm happy to extend. I want you to do the work. My intent is not to how do I pause share? My intent is not, I don't want anyone stressing of the homework. I want everyone to do it because that's the way that you learn in this course. But I don't want to inflict stress. And I realize that this homework is challenging. Okay, hold on. Let me just figure out how to content homework assignments. Let's say, just Sunday night is fine. Video solving the homework questions.
Yeah, that would be also helpful because the answer key usually doesn't have steps in it. So if someone made a mistake, they don't know. So
Right.
answer
For
key.
which homeworks are you guys, most, for all of them or just a specific set of homeworks? This one definitely. Yeah. Okay.
And also
Yeah.
Seven
Yeah.
and Norton homework, the last question was so confusing.
Okay. Let me. So I have to stop my sharing again. I have to make notes of this. Okay. Uh. So the right. Yeah, that's fine. That's not a problem. I don't know about a video, maybe, but I can definitely get you the step-by-step solutions. Okay. Let's see. Make 205. And last question of homework 4, is that what you guys said?
Yeah,
You're
the long
it-
Seven and Norton one.
okay.
Just like it had a lot of theory in it, asking about like comparison of Seven and Norton circuits, which I honestly and like most people I asked didn't know what was
Okay.
the answer for.
Sure. Kaya, I just saw your message. Um, yeah, so that's just an error. Um, you're not gonna lose points if I've excused it. Don't worry. It's just I either didn't communicate it to TAs or they didn't take it into consideration. But no one's gonna get. I'm not into. If I've said I'm not gonna penalize you, you won't be penalized. All right. So I think I've extended the due date to the 16th at midnight. That's Sunday night. Okay, let's delve into chapter 10. Sinusoidal steady state. So what does that mean? That means that you're looking at a circuit kind of at a single instant in time when everything's kind of converged. There are no more transients, all the um, you have circuits that are excited by sinusoidal batteries or sinusoidal current sources, and they have capacitors in them, they have inductors in them, they have resistors in them, and we are interested in solving for their steady state value. And so the good news is that everything that you learned up until now kind of comes together in this lecture. And so, for example, we're going to show you how to apply nodal analysis for AC circuits, so circuits that have sinusoids in them. We're going to show you how to do Thevenin-Norton's theorem, superposition, source transformation for AC circuits. And so there's basically 3 steps to all these problems. Step number 1 is to transform the circuit to the phasor domain. And sometimes it's done for you. On the exam, it has historically been done for you. And what that actually means is that every battery or every impedance is written as a complex number, not as not as 5 cos omega t, but like 5 angle 0, for example. Step number 2 is to solve the problem using the technique. So now your nodal analysis, for example, is going to be a linear system, like a linear system of equations, but with complex numbers. And so your matrix now will have complex coefficients, and you don't have to worry about, I'm letting you use a calculator. And if you get a calculator that lets you do complex numbers, you don't even have to worry about it. And so basically all the arithmetic now is with complex numbers. And then at the end of the day, when you have your solution as a phasor, let's say you're solving for a voltage at a node, and you have it expressed as a phasor, we ask that you transform it back into a cosine. And so sometimes step one is done for you. So if the problem is specified already in terms of phasors, you don't have to do step one. Step two is where all the work happens. Okay, so let's do an example to illustrate this. So this is an example where step one is not done for you, but we're going to show you how to transform everything. So you have a battery, resistor, inductor, capacitor, a current source, dependent current source, and then another inductor here. So remember, step one is to take all of these elements. We have 1, 2, 3, 4, 5, 6 elements, and convert them into phasors. So for example, the 20 cos omega t, the 20 cos 4t is just 20 angle 0, right? Because the phase angle of this sinusoid is 0 degrees, and its amplitude is 20. The resistors just stay as what they are. The resistor has no imaginary component, so it just stays at 10. The 1 Henry inductor is just J omega times L, where L is equal to 1 and omega is equal to 4, because the frequency of our source here is 4 radians per second. This inductor has an impedance of J omega L, where L is equal to 0.5 and omega is equal to 4. So J omega 4 is this impedance, and J4 is this impedance, and J2 is this impedance. And then finally, the capacitor, remember the impedance of the capacitor is 1 over J omega C. Here, omega is 4 and C is 0.1. So 1 over 0.4 is 2.5. And then we don't like the J to be in the denominator, so we move it up top to the numerator. So so the capacitor becomes negative J2.5. So just make sure everyone's clear. So this is here, this is here, this is here, and this is here. And so now you can rewrite this whole, you can redraw this whole circuit with complex numbers here, 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 and here. You're going to leave this as is for now. So on the next slide, I think we're going to see that circuit, hopefully redrawn. Yeah. So here's that circuit with complex numbers everywhere. So this is a phasor. So the value of this phasor is just 20, right? Because it has a real part of 20 and no imaginary part, but we can leave it as 20 angle 0. And so I should probably, just to expand on what I just said, if any of you can, 20 cos 0 plus J, okay, so this phasor, and I've already lost my cursor. Thank you, Zoom. Okay, so this phasor here just transforms into 20, a real number, because the sign of the phase angle is 0. So the imaginary term is just canceled or just is removed. Okay. And then we have a phasor for the inductors and a phasor for the capacitor. The phasor for the capacitor will always have a negative J on it. Okay, so that's just, if you have a capacitor and doesn't have a minus J in front of it, then probably you've made a mistake. Okay, now let's do nodal analysis. We have two non-reference nodes, node 1 and node 2. And let's apply KCL at node 1. So we have this current flowing in, right? So the voltage here is 20. The voltage here is V1. So this current here, I know it's going to cause problems. I'm going to just try to draw. Okay. So this current here is this here. It's just Ohm's law. This is 20. And 20 minus V1 over 10 is this current. And that's the current flowing into node 1. Now, what's the current flowing out of node 1? Well, we have two parts. One is this part, which is just V1 divided by negative J2.5. That's over here. And then the other part is V1 minus V2 divided by J4. That's here. And so you will be faced with a situation like this, where you have fractions that involve complex numbers. So one easy way to do it is just you can swap J between the numerator and the denominator just by flipping the sign. So this fraction here can be written as V1 times J over 2.5. Because if I can move the negative J to the top and call it positive J. Similarly with this J, I can move it to the top, the numerator, and stick a negative sign in front of it. Okay, so, and then once you have the J's in the numerator, you just do as you always do. You find a, whatever it's called, least common multiple, greatest common denominator, whatever. And then you just isolate your V1, your node voltages on one side and your coefficient on the other side. And so now, as if you're constructing a matrix equation for this, it will look something like this. So this is going to be a 2x2 matrix. And right now, by applying KCL at node 1, we have one of those equations. So we have V1 and V2. And the first coefficient here, I'm going to use text, is 1 plus J 1.5. And the second one is going to be J, oops. So this is the coefficient on the V1 term, and this is the coefficient on the V2 term. And this is going to be 20. So that's, and this, just because a matrix has complex numbers, doesn't mean that you can't do the same tricks as always. If you want to do row reduction, if you want to do matrix inversion, if you want to do, my God, how can I already forget the name of that method that the book uses? I want to call it Euler's theorem, but that's not what it's called. Kramer's rule. You can use Kramer's rule. You can do whatever you want. Or if you have a calculator that can solve the equations on the final exam, if you're asked to do it, you can. Okay. So the other thing you need to do is notice that Ix is the 2I, we have a current source whose I is 2Ix over here. So we need the value of Ix in terms of a node voltage. But it's obvious here that Ix is just equal to the current flowing down here, which is V1 over negative J2.5. So now, so that's one thing. The second thing is then the KCL equation at node number 2. which is V1 minus V2 over J4, that's here. Let's see. So we have this current, all right, 2Ix. So we have flowing in, we have this current flowing in, and this current flowing in, and then this current's flowing out. So the current that's flowing out is V2 over J2. That's here. This current here is V1 minus V2 over J4. And then this current here is 2Ix, which is 2 times this. So it's 2 times V1 over negative J2.5. So this current is here. And then this current, oops, is here. And so it's the same logic as before, where you're just applying KCL at every non-reference node. In this case, there are 2. And again, you're going to move the J's to the numerator, and you're going to determine the least common multiple, which here I believe is 10. And then you just you cross multiply, and you get 11 V1 plus 15 V2 is equal to 0, which means that now you can put your coefficient here. And so now you have 2 equations and 2 unknowns. And so the easiest way to do this, if you have access to a MATLAB terminal or a calculator that lets you invert matrices, it's going to be the inverse of this matrix. And the inverse of a 2 by 2 matrix, you can easily derive it. There's a nice and easy rule for it, which I won't get into here, but basically it's the inverse of this matrix, which is just another matrix multiplied by the coefficient vector. And so at the end of the day, you're going to get a complex number for V1 and a complex number for V2. And I believe that that's what we're going to see on the next page. Okay, so you put these equations, and they do Kramer's rule, which you can do, but you don't have to do. But at the end of the day, you get a complex number for V1 and a complex number for V2. In this case, you get a phasor that has a magnitude of 19 and a phase angle of 18.4 for V1, and a phasor that has a magnitude of 14 and a phase angle of 198 degrees for V2. And we know that Ix is equal to V1 over negative J2.5. So we need to take this phasor and divide it by negative J2.5. So remember last class we talked about that dividing and multiplying phasors is easiest done in polar form. So we need this phasor, this complex number is really expressed in Cartesian right now. So we need to convert it to polar form. And so just to convince you that this is in fact the polar form representation of negative J2.5. If this is the J-axis, then negative J2.5 is just a vector that points 2.5 units down the imaginary axis. Right? So the angle between the x-axis and that phasor is indeed negative 90. And obviously the length of that phasor is 2.5. And so now, if you have both V1 and the denominator expressed as a polar number, you can just divide the magnitudes and subtract the phase angles. So you have a magnitude of 7.6 and a phase angle of 108.4. And so the only thing that is new here is that the nodal analysis is all performed with complex numbers. And we are actually going to do the example that we're going to do next. We're actually going to carry out the complex math, which may be helpful to you guys. Okay, let me just quickly, just for a second, let me get out of slideshow. We are going to do an example practice problem. Okay. Let me see if I can make this really small. So we are presented with a nodal analysis problem. Okay, so the first thing that we have to do, remember, is to convert all of our circuit elements, so our current source, our capacitor, and our inductor, into phasors. So who can help me, first of all, convert 10 sine 2t into a phasor?
(10⁻90).
Excellent. 10 to the negative 90. I believe that was, yeah, 10 angle not negative 90 because, you know what, I'm just going to free draw all of this. So because the phase angle, remember, you have to express all your phase angles with reference to a cosine. So this is 10 angle negative 90. And what's our omega here? What's our frequency in this problem?
Two.
2, right? And so this here, this capacitor here becomes 1 over J times 2 times 0.2. So that becomes negative J times 2.5. And this, what about, who can tell me the impedance of this inductor?
For J.
Yep, thank you. It is equal to 4J. And I believe that everything else can stay because the rest are resistors. Yeah. So now we just need to, we're going to label our currents and just let's label them going this way. And we're going to do KCL at node 1. So KCL at node 1 is going to be, oh, I don't know how to do the angle sign. Let me just do this for the angle. So it's going to be 10 negative 90, right? Because that's the current that's flowing in here, is equal to V1 over 2 plus, so V1 over 2 is this current here. We have some questions. Oh. Am I frozen? Okay. Okay, good. Usually it tells me if Zoom is pretty good at telling me when I'm having internet problems. Okay, so let's try that again. Let's do KCL. And so we have 10 angle negative 90 flowing in is equal to V1 over 2 plus V1 minus V2 over negative J times 2.5. And so this is this current. That's Ohm's law. This is this current. And this is this current. So now let's manipulate, let's do this complex manipulation. Let's see. What did I do here? I multiplied, I moved everything to a common factor of 5. Plus J times 2 times V1 minus V2. Okay. So hopefully everyone understands that the only thing I did to go from here to here is I multiplied everything by 5 and I moved the negative J to the top and made it a positive J. And then call it J50 is equal to, let's see, let's put all the coefficients together, plus J2 minus J2 times V2. Yes. See if that's right. I believe it is. Yeah. So this here is our oops. Yeah, so this here, what I highlighted before, is our first equation that's going to go into our matrix. Let's do now KCL at node number 2. So we're going to have, again, V1 minus V2. And I'm drawing everything with capitalized V's to denote that everything, we're working with phasors now. So this term here is this current, left to right. That's flowing in and flowing out is V2 over J4 plus V2 minus, put V2 minus 3Vx over 4. And so who can tell me now what Vx is equal to in this problem? What's the relationship between Vx and the node voltages that we have, V1 and V2?
Vx equals to, V1 over 2.
Vx is just equal to V1. Because this is 0 voltage. This is Vx volts, right? Because there's a voltage rise of Vx from here to here. So Vx and V1 are actually equivalent. And which means that now we can, let's see, rewrite the previous question the same, and we're just going to rewrite it with plus, I'm going to stick in V1 for Vx. Okay, and I am going to use a common multiple of 10. Okay, so I'm going to multiply everything here by a factor of 10. I'm going to move all the j's out of the denominator. So that's going to be 4 j4 v1 minus v2 is equal to negative j times 2.5 times v2 plus 2.5 v2 minus 3. Let's just expand it to 2 minus 7.5 v1. And now what I'm going to do is I'm going to collect all the like terms. So I'm going to, let's see, let's take all the terms of v1. So we're going to have, v1 is going to have j4 plus 7.5. And then v2 is going to have, let's put a minus sign here, j4 it's going to be 2.5 plus 1.5j, I think. I believe this is right. Let me just check my notes here. Yeah, that is correct. Hopefully you can all convince yourself that to go from here to here, all I did is move stuff from the right side, the right-hand side over to the left-hand side. And now I am finally ready to make my matrix. All right, so I'm going to draw my matrix. I'm going to stick in my complex coefficients. And you, by the way, you can do the method of substitution with complex numbers. It's just a little bit more work, but you can absolutely do it. So this is going to be 2.5 plus j2. This is going to be minus j2. This is going to be 7.5 plus j4, going to be minus 2.5 minus j 1.5. This is b1, b2, and this is minus j 50, and this is 0. And so, you can solve this by just rearranging one of these equations. Let's say in this equation, isolate for v2, and then plug that into v2 in the second equation. That will give you the answer. In terms of what the numeric answers actually are, you will see that v1 is going to be equal to 9.8 minus j times 5.66, and v2 is equal to 27.7 minus j 17.9. Okay, so now we have the numbers in complex form. So actually, the first thing I want to do, I'm going to actually show you how I do this. Open up my MATLAB window. Get it to open. Oh. I'm going to show you a quick way of Oh, I don't want to erase everything. All right. Anyhow. I want to leave the matrix intact. Okay, so I'm going to make my matrix first of all. I'm going to enter my matrix. The notation is in MATLAB, you use square brackets to enter a matrix. Use commas to go across a row. And you use a semicolon to enter the next row. J times 4. That's my matrix M. And my coefficient B, my coefficient vector B is just negative J50 times 0. Okay, now if I enter these, you will see that I've entered my coefficient matrix M. Hopefully I've entered it right. I should check it. Looks right. And I enter my coefficient vector B. That looks right as well. And if I want the answer, you just go M divided by B. And here is my solution, which hopefully matches what I had on my PowerPoint slide. And I'll tell you that my solution, and it does. Right, so this is the number, this is the solution to the answer as a complex number. Now, what we need though, at the end of the day, we need to convert these complex numbers into a magnitude and a phase angle. And so let me just store this. And what I'm doing now, you could do on a calculator, you could do with pencil and paper, but what I'm going to do is figure out the phase angles and magnitudes that this corresponds to. Okay, so let's go step by step. So these are the magnitudes. These are the phase angles. Okay. And so X is the solution where X has two elements. Element 1, this is a solution for V1. And element 2 is a solution for V2. And those are expressed as phasors. They have a real part and an imaginary part. But I want their magnitudes. So in MATLAB, to get a magnitude of a complex number, you can use the abs function. And to get the angle, you can use the angle function. And to convert from radians to degrees, you multiply by 180 over pi. And so what you see here is that the first, let me see if I can write over this now. The first voltage, V1 of t, is going to be equal to 11.33 cos 2t, because 2 was our frequency, minus 29.98 degrees. And V2t V2t is going to be equal to 33.02 cos 2t minus where is it? 32.87 degrees. Okay. And so again, what I just showed you is just that if you have the matrix equation, which is this, which is just the MATLAB implementation of our system of equations. If you solve for the unknowns, which here are V1 and V2, those unknowns come out as complex numbers. And because they're complex numbers, you can easily convert them to into polar form. They're basically the polar form representation, where these are the magnitudes of the polar number, and these are the phase angles. So this is the magnitude of V1, magnitude of V2. It's the angle of V1 and the angle of V2. All right. We are behind on time, but that's okay. Hopefully you guys learned something from having that one done step by step. Let's move on. We're going to skip this. We're going to go on to this one. So here's an example where everything's already in phasor form. So you don't have to convert anything to phasors. It's already converted for you. So what do we call the connection between V1 and V2? What is the name that we've used in this course for this?
Supernode.
Thank you. Supernode is correct. Right? And so we have a supernode. This one's easy. 1, 2. And so let's write the, first of all, let's draw the currents. We're going to draw them going this way. We're going to draw this one going in, and everything else we're going to draw flowing out. So we have one current flowing in, that's over here, and everything else we're just going to call flowing out. And then let's write the KCL equation at supernode. We have 15 angle 0. Let me just put the parentheses. 15 angle 0 minus V1 over 4 is this current. And the current orienting down through the inductor is V1 over J4. Then we have V2 over negative J plus V2 over 2. And so this just becomes 15 minus V1 over 4 is equal to negative J V1 over 4 plus J V2 plus V2 over 2. We just divide everything through by 4. We get 50 minus V1 is equal to negative J V1 plus J2 V2. That's right, plus 2 V2. Okay. And now when we rearrange this, we get V1 has, let's see, negative 1 plus J, I believe. Let's move it to the other side, actually. So that's our equation. That's our KCL equation at node number 1. Sorry, at the supernode, my bad. And so again, there's nothing new here. The only thing that differentiates what you did in lectures 4 or lecture 3 in this is that we have complex coefficients for everything, but the concepts are identical. And then there's the KVL at supernode. So who can tell me the KVL equation at the supernode here?
V1 minus V2 equals 20 angle 60.
Excellent, thank you. That's it. That's our second equation. And now we can put everything into a matrix. So our coefficients here are going to be 15 so sorry. I didn't make it to the mute button. Allergy season. 20 angle 60 over here. And this becomes 1 minus j 2 plus j4 becomes 1 negative 1. This becomes v1 and v2. And by the way, if you're wondering how to express 20 angle 60 as a complex number, so 20 angle 60 equals 20 cos 60 plus j times 20 sine 60. And that's gonna, a cos of 60 is half, I believe. 10, so this becomes plus root 3 over 2, I guess. That's equal to 10 plus j, 17.32. So that's what this is going to become. And when you're done with it, you get that V1 is equal to 19.36 angle 69.7, and V2 is equal to 3.38 angle 165.7. So if the question is specified with phasors, you can leave it, oops. Oh, come on. All right, I'll write it again. So what I was saying is that if the question is given to you in phasor notation, unless I specified otherwise, you can leave your answer in phasor notation.
Professor, in the exam, are you gonna do like class midterm that you're only asking for the matrix, or you're gonna ask for the actual answer?
I've historically just asked for the matrix,
Okay.
especially with complex numbers. I'm not really testing your I'm not testing your you know, your complex math skills. Okay, let's move on to, first of all, let me stop here and pause it. If there's anyone that has questions about what we're doing, please let me know. Okay. Mesh analysis. So there's no new theory behind this. It's just we're going to do an example of a mesh problem. Let's see. We'll do this one. Okay. So let's draw our meshes. Let me see if I can zoom in a bit more. If we have more of my space. All right. So let's, you know, if you remember mesh analysis, we will have a mesh I1, and here the I's would be phasors. And we'll draw them going this way. So everything's going to be going clockwise. We'll call this I2. And we'll call this I3. Okay. And so now let's write the mesh, the KVL for mesh number 1. All right, so who can help me with mesh number 1, the KVL equation for mesh number 1?
would it be 8I1
Yeah.
times negative J2 negative J2I1
Mm-hmm.
plus J4 times I1 minus I2. I2 minus I1.
No, you're right. It was my bad. It's right. You're right. I1 minus I2. Excellent. And so that transforms into I1 with a coefficient of 8 plus J2 plus I2 and J4 is equal to 0. Right. And the way to do this, if you add up all the impedances around this loop, it's 8 minus J2 plus J4. So the net sum is 8 plus J2. And then this is the amount that is common to meshes 1 and 2. So that's equation 1. And who can now help me with the KVL for mesh number 2? Okay, so I'll just, I2 is entering here. So there'll be J4 times I2 minus I1. Make sure I got this right. Plus 6 times I2 minus I3 plus 10 angle 30 is equal to 0. Okay, and so that transforms into I2 with a coefficient of 6 plus J4 minus I1 with the coefficient of J4 angle 30 minus 6 I3. And let me just double check that. Okay, so let's add up all the impedances around this. J4 plus 6. So that is the coefficient on mesh 2, on I2. Now, how much is common with mesh 1? J4 is common with mesh 1. So it makes sense that this is the coefficient on the I1 is minus J4. And how much is common between meshes 2 and 3? 6 is common. So we stick in a minus 6 coefficient on the I3 term. And so we can move this minus 10 angle 30. And minus 10 equals 30 is equal to minus 10 times cos 30, oops, plus j sine 30. So that's if you want to express it as a complex number without the polar notation. Let's see. And what about what can we say about I3?
It would be equal to -2.
Exactly. Right. And so what we do here is we can plug in this into here. So that becomes plus 12. And then so that term becomes like a constant. This becomes I2 6 plus J4 minus J4 is equal to all of this negative 10 cos 30 plus j sine 30 minus 12. And so now we have our two equations. We have equation 1 here. We have equation 2 here. And we can again draw our matrix. Okay, we're not solving for voltages, but we're solving for currents. So we have I1, I2, and then this becomes 8 plus J2. Remember, that's from over here. Becomes minus J4. Becomes minus J4. This becomes 6 plus J4. And the coefficients are 0. And this thing here becomes negative 20.66 minus J5. You'll just have to take my word for it. So the minus J5 is because the sine of 30 is a half. So a half times 10 gives you 5. And then this becomes whatever this is minus times 10 minus 12 gives you negative 20.66. And then when you solve this system of equations, you get that I1 is equal to 1.19 angle negative 114.55, and I2 is equal to 2.46 angle 169.48. And then I naught is equal to negative I1, right? So we are asked to solve for I naught. And notice that I naught is the same current as I1, just in the opposite direction, right? So the relationship between I naught and I1 is that they are the same current, just flowing in the opposite direction. And so this brings up a legitimate question. So what if I have a phasor like this, and I need to negate that phasor? This is actually a good question for you guys. If I have this number, it's in polar form, and I want to negate it, how do I write this with a minus sign in the front of it? There's an easy way and there's a hard way. I mean, there's a short way and there's a long way.
Did you just add 180 degrees?
Yes, that's terrific, Ben. That's great. That's really great. The hard way would be to convert this to a Cartesian number, multiply everything by multiply the real and imaginary part by -1, and then to convert back. But you correctly identified that if you have a phasor, right, if you have a phasor whose length is 1.19 and whose angle is -114, so that's like over here and flowing, pointing this direction. So when multiplying it by -1 is just equivalent to turning it this way. So it's going to have the same length, but now you're just going to add 180 degrees to it. So instead of being -114, it becomes +65. So that is a really easy way. If you ever have a phasor and need to negate it, you just add 180 degrees to it. And if you wanted to convert this back into a cosine, it will be into like a cosine function. It will be 1.19 cos. Well, actually, we wouldn't even have the omega here. But if you had the omega, it would be like that. All right. Moving along. This is an example. All the examples are done for you. Okay. Here's an example of mesh analysis where again, all the phasors are done for you. But the big difference is that here we have a super mesh. We have a super mesh between meshes that I'm going to call this I1. I'm going to call this I2. And I'm going to call this I3. All right. And the first thing that we're going to do is do KVL around the mesh that doesn't include the super mesh. KVL at mesh 1. And so KVL mesh 1, we're going to start over here and we're going to work around. So maybe I'll just highlight the path here that we're going to take. It was Mother's Day recently, so I'm going to use pink. I guess I should have used it on Monday. And also, I'm not sure this is pink because I'm colorblind. But this is the path that we're tracing. Okay. So we're starting over here, -50 plus 10 times I1. And then now this node, this branch is shared between meshes 1 and 2. So we're going to have to go -J4. It's going to be I1 minus I2. I believe that's right. And then finally, there's this branch, 5 I1 minus I3 is equal to 0. Okay, so the voltage rise of 50, a drop of 10 I1, a drop of -J4 times I1 minus I2, and a drop of 5 times I1 minus I3. And that becomes I1 times 15 minus J4 plus I2 times J4 minus 5 I3 is equal to 50. And so that is our first equation with 3 unknowns. Okay. And now we get into the super mesh. So remember that for the super mesh, is here for this problem. And we're going to cut the circuit. We're going to cut this off here. So we're just going around the periphery. Okay, so we're going to do KVL around the super mesh here. Okay, so we can start really anywhere we want. Let's start over here. Let's start at the top of the diamond. We're going to do J8 times, let's do I2 times J8 minus I3 times J6 plus, oh, I have a question. Thank you, Christian. That's awesome. They really need to make it so that I have like a split screen where I'm teaching and then on the side is the chat. It's like whenever if any of you guys watch sports, on certain sites that stream sports, and you have the chat on the side so you can watch and chat with your friends at the same time.
You
That'll
can,
be
Professor, but you need to have two screens for that.
yeah, I could. But you know, the reason that I don't actually is because I cannot annotate the screen and be in the chat window at the same time. So if I go on the chat, then like if I have the chat window active, then it will not let me annotate. So I have to, the annotation immediately goes off. So I don't, at least if there's a way to do it, I haven't found a good way, but that's okay. So let me just see if Christian's answer here was right. 5i3 minus I1 minus J4. Yeah, that's excellent. That's right, Christian. Let me just erase this. Start all over. So it's going to be J8 or I2 J8 minus I3 J6 plus 5 times I3 minus I1 minus J4 times I2 minus I1 is equal to 0. And when you collect the like terms, you get, this is the coefficient on I1, coefficient on I2, coefficient on I3. Okay, and now I will get your help, hopefully, to help me with the KCL at the supermesh. So let's take this node here, okay, that node. What is the KCL equation at this node? I3 plus I2 is equal to 2. Let me see.
Isn't it I2 plus 2 equals I3?
Yeah, I believe so. Yeah, so it's this one. So I'm just gonna add, I'm gonna draw it. It's gonna be, this is flowing in, and then these two are flowing out. So it's I3 is equal to I2 plus 2. But that was very close, the answer, Christian. Just, it's easy to get these mixed up. And so now we have, but we do have now the 3 equations and 3 unknowns. So our matrix is going to be so this is 15 minus J4. And this is J4. This is minus 5. This is a 3x3 system, which you will want to solve, you know, some kind of numerical technique. It becomes 0, -1, and 1. And the unknowns here are I1, I2, and I3. And the coefficients are 50 0, and 2. And when you solve this, you get that I1, we're really interested in the I1, because the thing that we're asked to solve for I0 is equal to I1. I1 is equal to 5.07 angle 5.94. So magnitude is equal to 5.07. Phase is equal to 5.94 degrees. All right. Let's move along. Superposition. So a little bit of theory. So basically, remember, superposition is a technique where you solve a circuit one source at a time. So if you have multiple independent sources, then you leave one of them on at a time. You disconnect the other ones. You solve for the first circuit. And you store that solution. Then you turn off that source, leave the second one on, solve it, store that solution. And then at the end, you add up your individual solutions. Now, the only kind of new concept here is that superposition becomes necessary if you have more than one frequency in the circuit. And so, for example, if you have a circuit that has a battery operating at omega is equal to 2, and another circuit that is operating at omega is equal to 4, you have no choice but to apply superposition. You cannot solve that circuit by transforming it into phasors, because phasor domain notation implicitly assumes that you're working with one frequency. And as soon as you have a second frequency introduced, then your phasor is no longer correct. So you solve for one frequency at a time, and then at the end, you convert your answer back into a sinusoid and you can add up your answer. And so this will all make sense when we do a couple of examples. I'm going to skip the one that is solved for you, and we're going to do the practice problem over here. I will do the same thing as before. Just move this over. I should get rid of. Give myself a lot of room here because I will need it, because I will have to solve this problem twice. But each time it will be a simpler circuit. Hopefully I can fit everything. Hopefully I can fit everything onto the slide here. Okay. So let's first, let's see, which source are we going to disconnect? Let's disconnect the current source first. And maybe I can actually benefit from Zoom. Guess I have to select the color first. Okay, so that's my circuit. There's nothing up here. And I am interested in finding this current here. So without telling me exactly how, without getting into the mechanics, what technique could I use to solve for I naught?
Mesh analysis.
Mesh analysis is a rational choice, absolutely. But I'm not a big fan of mesh analysis, and I'm lazy, and I don't want to have to I don't want to have to deal with a system of equations. Is there any other way that you can think of that that we could do this?
Could you combine all the things?
Yeah, that's right. Combining the resistors. Current, yeah. So there's some good answers here. Current division. It is. I think it could be done at current division at the end. So what we're gonna do, and there are many ways of solving this. There's many sequences of steps. Basically, what I do is I note that these two impedances. So I'm gonna combine the. Let's see. So this is 8 minus J2. Okay. And that's in parallel with the J4. And so I'm going to define, just going to call it Z2 is equal to J4 in parallel with 8 minus J2. Right? Because this combined branch here is parallel with J4. Hopefully everyone agrees with that. And I'm gonna, because we don't have a ton of time. So I am gonna show you how to, you want to do product divided by sum. So you're gonna multiply these complex numbers and divide by their sum. And Z2, when all is said and done, is equal to 1.88 plus J times 3.53. Okay. And so now, now basically we have the battery. Let me draw this. So we have our battery. We have our 6 ohm impedance. And then we have our Z2. This is Z2. So now what technique can I use to solve for the voltage drop across Z2? I'm going to call that V2. What technique, given that this is 6 and this is 10 angle 30. Right, so what I've done in the first step, what I've done over here is I've combined this, and this into a single impedance that I've called Z2. And I want to know the voltage drop across that impedance, which is really the voltage over here. What technique can I use? So I can use voltage division. Let me just. So it'll be 10 angle 30. So I can say V2 is equal to 10 angle 30 times Z2 over Z2 plus 6, right? Because the sum of the impedances is Z2 plus 6. So again, I'm going to spare you of the mechanics. I'm just going to tell you what the answer is. It's going to be 1.7 plus J times 4.29. So that is the voltage over here, which means that the current I naught, so Ohm's law, says that I naught is equal to V2 over 8 minus J2. So I naught is equal to 1.75 plus J times 4.29 over 8 minus J2. And it works out to be 0.56 angle 81.08 degrees. Okay, so again, the sequence of steps is the complex arithmetic is not the important part. Don't get lost in that. The important part is what I've done at the very beginning, where I've collapsed, I combined the 8 and the minus J2 into a single impedance. And I noted that that single impedance is in parallel with J4. So I simplified into a single impedance that I called Z2. And then my circuit is just the battery, the 6 ohm resistor, and that Z2 impedance. I use voltage division to get the current across this combined load. So the reason that I couldn't just do Ohm's law here to get the current is because Z2 contains 2 branches in it, really. Right? Z2 is really modeling all of this. And so I had to unpack the circuit at the end, figuring out that V2, the voltage that I solved for here, is the voltage at this point in the original circuit. And then I just divided by the impedance using Ohm's law to get the expression for I naught. All right, let me now, we are going to disconnect the battery. This is the second step here. So to disconnect the battery, this, but we also need to, okay. And so for this circuit, I need to come up with an expression for I naught here. And because we only have 6 minutes left, and I would like to get to the problem, it's going to tell you that we're going to use nodal analysis. This is node 1 and this is node 2. And this here at the bottom, this is ground. And so so this here is V1. And this here is V2. And let's draw the currents going this way. I'm going to draw the currents going like this. And now, so here we disconnected the voltage source. And we're going to apply KCL at node 1. So we have V1 over 8. That's this current here. This is V1 over 8 is equal to V2 minus V1 over negative J2. Parentheses. So in other words, this current flowing down has to be equal to the current flowing from node 2 to node 1. And that ends up being V1 times negative 8 plus J2 plus V2 times 8 plus V2 times 8, and that's equal to 0. So that's node 1, pretty straightforward, only two branch currents there. Node 2 now, it's a little bit more involved because now we have one current flowing in. Oh, actually, I think no, we have 4 currents at node 2. And so I've actually, let's see here in my solution. This isn't the best practice, but it is technically correct. I just noticed that for node 2, I had the current drawn this way, which isn't great. Again, it's not great, but there's nothing incorrect about it. I reversed the direction of the arrow. And so And I'm gonna have two currents flowing in, left to right here and downwards, and two currents flowing out. This one flowing out and this one flowing left to right. So let's write the KCL equation at node number 2. So that the current that I've just written here is the current flowing from V1 to V2. And the 2 amps over here is also flowing into node 2. Flowing out, we have V2 over J4 plus V2 over 6. Okay, and that, after collecting like terms, becomes that. And so we again have a system of equations. Some it's just a two-dimensional system in V1 and V2. So we have -8 plus J2. We have 8. We have negative J3 over here. And we have 1 plus J1.5 over here. And this is V1, phasor V1. This is phasor V2. And the coefficients are 0 and 12. Okay. And when you solve all of that, when you solve this two-dimensional system, you get a solution for V1 of 5.39 magnitude and 51.8 degrees phase angle. And what that means is that I naught is equal to V1 over 8. So it's going to be equal to 0.67 angle 51.8. So now we have two solutions for I naught. We have 0.56 angle 81.08 and 0.6 angle 51.8. So the final solution, right, because this is superposition, is equal to the sum of these two. And that works out to be 1.19 angle 65.44. And so if you're wondering how I added these, there's a couple of different ways you can add them. The easiest way is to convert them into Cartesian. And so for example, I naught would be equal to 0.56 cos 81.08 plus 0.56 j sine 81.08 plus 0.67 cos 51.8 plus j 0.67 j sine 51.8. And so to add these two numbers that are in polar form, the easiest way is to simply convert to Cartesian. And then once you have the number in Cartesian, you can convert it back into polar form. Okay, I think for the first time ever, I've actually run overtime. So we will wrap up lecture 10 next Monday. I believe we're also going to do one lab module. I'll talk more about the final exam. I've extended homework 5 until Sunday night, and I'm making a commitment to solving homework 5 for you guys in the next week or so, less than a week or so. I wish you all a pleasant weekend. Thank you for sticking around, and see you for the last lecture of the semester on Monday.